In this deck, we focus on export stowage planning, which is the task of deciding exactly where each export container should be placed on a vessel before departure. The decision is not only about fitting boxes into slots, it is about building a plan that stays safe and efficient across a multi-port voyage. Export stowage matters because a single port placement can force extra container moves at intermediate ports, slow the vessel's turnaround, increase fuel consumption through poor trim, and create safety risks through unstable weight distribution. The goal is to place export containers into vessel slots to minimize overstowage and maintain safety. The plan must respect stability, hazardous segregation, reefer accessibility, and a multi-port discharge order. Operationally, the plan is judged by whether it avoids costly restowage at intermediate ports while keeping the ship within safe stability and structural stress limits. Overstowage happens when you must move containers just to access other containers below deck. That is expensive because it consumes crane time, creates extra yard reshuffles, and increases the chance of missed sailing windows. In export stowage, the main driver is discharge order. Containers destined for earlier ports must remain accessible, and containers for later ports can be placed above them. The stowage plan must remain safe across the entire voyage. Stability constraints include center of gravity behavior, metacentric height limits, and trim limits. Structural limits also matter, including shear forces and bending moments along the hull. Hazardous cargo must satisfy segregation rules, and refrigerated containers must remain accessible for power connections and inspections. The scenario centers on the vessel MSC Gülsün, with a capacity of 24,346 20-foot equivalent units. The vessel arrives to load 8,500 export containers bound for 12 ports. The ship has 22 bays with bay row tier slot coordinates. This coordinate system is the language of stowage. Every placement is a specific bay, a specific row, and a specific tier. Stowage uses a bay row tier coordinate system. Bays define longitudinal sections along the ship, rows define port versus starboard positions, and tiers define vertical stacking. A good plan is consistent. It supports discharge order, keeps reefer containers accessible, and places heavy containers where stability allows. The coordinate system is the framework that makes those constraints enforceable. Each container differs by size, weight, type, and destination. Stowage must keep the center of gravity inside safe limits and control hull stress, not just at departure, but throughout the voyage as containers are discharged. At the same time, the plan must minimize hatch overstowage, meaning you must avoid burying early discharge containers beneath later discharge containers. Hazardous materials add an additional layer through segregation distances and compatibility rules. Bay 14 is designed for 40-foot containers. The slide gives an example slot coordinate range from 140282 to 141090. A refrigerated container bound for Singapore cannot be buried beneath heavy containers destined for Dubai because Dubai is discharged earlier. Burying the reefer would force restowage, creating both cost and operational delay. This deck is organized into tiers that escalate capability. Tier 1 frames stowage as a Markov decision process. Tier 5 introduces an integrated digital twin. Tier 7 introduces a human and artificial intelligence partnership for collaborative planning. Tier 9 introduces a quantum optimization framing. Tier 11 explores a long-term vision using programmable matter. Tier 1 models stowage as sequential placement decisions. At each step, you choose a container and an allowed slot. Rewards penalize overstowage risk, stability impact, and time cost. This captures the central trade-off. A placement that is good for discharge order might be bad for stability, and the policy must balance both. Stowage decisions are sequential. Each placement changes what is feasible next because it changes stack heights, hatch accessibility, and weight distribution. Uncertainty can be represented through future arrivals or last-minute cargo changes. The Markov decision process view helps you reason about long-term consequences, not just the next best-looking slot. This slide defines the state as a tuple capturing 5 elements. The first element is slot occupancy, which tells what is already placed where. The second element is the center of gravity coordinates, which summarize stability. The third element is the set of containers still awaiting placement. The fourth element tracks hatch accessibility requirements by bay. The fifth element is the discharge port sequence, which defines the precedence logic for accessibility. The action space is the set of valid placement decisions. Each action chooses a specific container and assigns it to a specific slot that is valid given the current state. Operationally, valid slots depend on container size, container type restrictions, available power for reefers, segregation rules for hazardous cargo, and physical stack rules. The transition function represents what happens after you place a container. In the simplified version shown, placement is deterministic. The next state is the result of applying the placement action. In practice, you can also treat future container arrivals as stochastic, which makes planning more robust to late cargo and operational variability. The reward function penalizes overstowage cost, stability cost, and time cost. Overstowage cost captures the expected future restowage required at intermediate ports. Stability cost penalizes unsafe or inefficient weight distributions, and time cost penalizes operational complexity that slows loading. This slide defines the goal as finding an optimal policy that maximizes expected cumulative reward across the full sequence of placement decisions. Operationally, this means you are not optimizing only the departure condition. You are optimizing the plan's behavior across future discharge events and future operational constraints. Overstowage cost is driven by the number of extra moves required at intermediate ports. A placement that blocks earlier discharge containers creates predictable future rehandling. This is why discharge order is often reflected either directly in the reward or indirectly in feasibility rules that prevent burying early discharge cargo. Stability cost penalizes placements that shift the center of gravity outside safe limits. It can also capture hull stress proxies, such as excessive imbalance across bays. Even if a placement reduces overstowage, it must not compromise safety margins. A plan that is operationally convenient but unsafe is not acceptable. Hazardous containers must maintain required segregation distances and compatibility rules. These rules can eliminate many apparently good placements. In practice, segregation is enforced through allowed slot filtering and penalty terms. The stowage planner must treat these as hard safety requirements. Feasible placements must respect stack weight limits so that no stack exceeds its safe load. They must also respect stability margins for metacentric height and trim. They must enforce hazardous segregation distances and hatch accessibility rules to limit overstowage and ensure that intermediate port discharges are possible without excessive rehandling. This slide summarizes the constraint categories that govern feasibility. Operationally, the key message is that the stowage plan is not only about packing density. It is a safety-constrained, multi-port accessibility problem. This figure provides a cross-section view and stability structure. Use it to connect abstract stability concepts to physical reality. The placement of heavy containers low versus high and fore versus aft directly impacts stability and structural stress. The example uses 3 containers and 6 available slots. Container 1 weighs 25 tons and is destined for Singapore as discharge port 3. Container 2 weighs 18 tons and is destined for Dubai as discharge port 1. Container 3 weighs 22 tons and is destined for Mumbai as discharge port 2. Available slots are described using bay row tier identifiers like 140284 and 160284. The goal is to place the containers so earlier, discharge remains accessible while staying stable. Dubai is the first discharge port, so its container should not be blocked. Mumbai is second, so it should remain accessible after Dubai. Singapore is later, so it can be placed above earlier discharge containers. This simple rule of thumb mirrors how overstowage penalties emerge in practice. This slide shows a value function update step and a concrete numeric calculation that results in negative 22.2. Operationally, the value function explains why a specific placement choice is preferred when you account for immediate penalty plus the discounted future penalty. The example policy places containers in discharge order. Dubai is placed at the bottom tier, Mumbai above it, and Singapore on top. This reduces reswitch at intermediate ports and reduces overstowage penalties. It also keeps the discharge workflow predictable for terminal operations. Tier 5 connects a vessel to a live digital model. It integrates vessel sensors, container tracking, terminal operations, and weather. The digital twin supports continuous re-optimization and what-if analysis, which matters because stowage plans often need adjustments as the loading sequence unfolds. Vessel monitoring sensors track trim, stress, and weight distribution. Container IoT provides condition and location updates, including for refrigerated cargo. Terminal systems provide crane cycle times and handling constraints. Weather forecasts update stability and stress calculations, which can change what placements are safe or optimal. Hydrodynamic simulation updates stability, trim, and stress under changing load conditions. Container logistics simulation models cranes, vehicles, and transfer times. Multi-port route simulation optimizes the plan across intermediate ports, so the stowage plan is evaluated across the full voyage rather than only at departure. This slide shows the system of systems architecture for stowage planning. Operationally, the architecture matters because it enables consistent data flow. Without synchronized data, optimization results can be mathematically correct but operationally irrelevant. Weather impact simulation models how sea conditions affect optimal stowage patterns and structural stress. Port congestion modeling re-optimizes when intermediate ports delay operations. Equipment failure scenarios model crane or vehicle degradation and generate contingency stowage plans that reduce dependency on fragile resources. Hydrodynamic simulation is described as updating every 30 seconds. Structural stress measurements are described as updating every 15 seconds. These update rates enable proactive detection of unsafe loading patterns. The purpose is to catch risk early before the plan becomes hard to correct. The MSC Gülsün digital twin uses 847 IoT sensors. Weight verification accuracy is described as plus or minus 0.5%, and structural stress updates every 15 seconds. The system prevented 23 potential overstowage situations during a 6-month trial, saving an estimated $1.2 million. Fuel consumption decreased by 3.8% through optimized trim. Planning time reduced from 8 hours to 45 minutes, while improving stowage efficiency by 12%. Tier 7 combines human planner intuition with AI constraint checking and optimization. Explainable recommendations make trade-offs visible and auditable. Authority shifts depending on confidence and scenario complexity. The goal is to use AI for consistency and scale while keeping human expertise for exceptional cases. High-confidence AI domains include routine placements with clear constraint satisfaction, such as standard containers with obvious feasible slots. Human-led domains include exceptional cargo, complex hazardous combinations, and vessel-specific quirks. Collaborative zones cover moderate confidence cases where humans choose among several AI-generated scenarios. This slide visualizes human and AI collaboration and explainability. Operationally, the key requirement is that recommendations are not black boxes. The system must show why a placement is recommended and what risks it avoids. Constraint visualization shows why placements are feasible or unsafe, for example by displaying safety zones for hazardous segregation. Confidence scoring distinguishes stable recommendations from uncertain ones. Counterfactual explanations quantify cost increases from alternative placements, such as increased restowage cost at an intermediate port. A 6-month deployment across 15 vessels reports measurable benefits. It reports 28% fewer suboptimal stowage decisions compared to human-only planning. It reports 35% fewer constraint violations compared to AI-only optimization. It also reports a 15% improvement in planning time efficiency. The system captured 847 unique stowage tricks and identified 156 potential safety issues missed by either approach alone. Trust is calibrated using performance tracking across vessel types and cargo mixes. Humans provide feedback on explanation quality and operational usefulness. Disagreements are documented with outcomes so the collaboration improves over time. This prevents trust from being based on hype rather than measured performance. Tier 9 maps stowage to a quadratic, unconstrained binary optimization model. Quantum approximate optimization approaches aim to explore large configuration spaces efficiently. The key promise is speed for certain hard instances, especially when many constraints interact and the classical search space becomes enormous. A binary variable can represent a container slot placement decision. Quadratic terms encode interactions between placement decisions, such as blocking relationships or stability coupling. Penalty terms discourage infeasible configurations. Operationally, penalties encode safety and feasibility requirements that cannot be violated. This slide shows the quadratic unconstrained binary optimization form, where the objective is a sum of pairwise terms. The coefficients encode overstowage, stability, and segregation interactions, so the energy landscape reflects the trade-offs of different placement patterns. This slide expresses the idea of representing configurations in a superposition state. Operationally, it is a conceptual model. Many candidate stowage configurations are represented at once, and the algorithm aims to bias outcomes toward low-cost configurations. This slide shows a unitary operator composition used in a quantum approximate optimization style method. Operationally, the key point is alternating between an operator that encodes the objective and an operator that mixes between candidate solutions. This figure shows a quantum circuit architecture for container stowage optimization. The main takeaway is how the circuit encodes decision variables and interactions. The structure is designed so that measurement yields candidate placement decisions. The tier describes that for a vessel with 10,000 slots and 8,000 containers, a quantum approach reduces solution time from days to minutes. A hybrid quantum classical implementation is described as achieving 2.3 minutes for an 18,000 20-foot equivalent unit optimization versus 8 hours classically. It also reports 15% better solutions in large multi-constraint instances. This slide describes optimizing across multiple vessels and shared ports. The goal is to coordinate container flows so total system cost is minimized. It is described as previously computationally intractable with classical methods, especially when optimizing across the network rather than within a single vessel. Tier 11 imagines programmable containers and adaptive vessel structures. Containers can reshape, reconfigure internal partitions, and redistribute weight. The vessel itself can morph bays and adjust structural properties, creating a future world where stowage is no longer constrained by fixed geometry. Dynamic space optimization means shape and dimension changes to increase utilization. Load distribution intelligence means shifting internal mass to maintain trim and stability. Multi-cargo adaptation means internal subdivision and environmental controls, so a single container can act as multiple compartments or cargo modes. Morphing bay architecture can expand, contract, or reconfigure for unusual cargo. Adaptive structural elements alter rigidity under heavy weather. Dynamic stability systems adjust continuously without manual trimming operations. Operationally, this removes many constraints that drive today's stowage complexity.